Vanakkam. Welcome to this course on biomedical instrumentation. In the previous set of videos, we looked at the origin of biopotentials, we looked at the various equations regarding electrochemical equilibrium, for example, Nernst equation, GHK equation, card conductance equation, etc. And then in the previous video, we looked at action potentials. Once again, these are only giving you a brief introduction to these physiological principles. For a deeper understanding, I request you to refer my previous courses or other material, other textbooks or other materials on the web for your improved understanding. What is discussed here is just sufficient for you to do biomedical instrumentation. So, because this is a course on biomedical instrumentation, not on membrane physiology or physiology. So, we will have to move on to other topics. In line with that thought, in this video, we will look at biopotential electrodes and we will look at the electrode electrolyte interface and the half cell potential that is generated in the at the electrode electrolyte interface. Now, what are these biopotentials? These are essentially transducers that achieve a great task. What is this task? Note that the currents that happen inside the excitable cells are ionic in nature. Physically, ions move from, say, the inside of the cell to the outside of the cell, or from one part of the cell to another part of the cell, and all. This involves physical movement of ions. Whereas, our measurement systems are all electronic, in which case movement is through electrons, that is why it is called as electronic. So, you are interested in converting these ionic currents into electronic signals that can be measured using analog and then maybe converted to digital and stored and then processed. This is my interest. So, ionic currents need to be converted into electronic signals that can be processed by the instruments that we have, biomedical instrumentation systems. But why do we need them? Why do we need these biopotential electrodes? Because human body does not generate electricity through electronic means, but rather through ionic potentials. Human body's electricity, bioelectricity is through ionic potentials and through electrochemical activity, whereas the measurement systems that we have are all amplifiers, recorders, computers are all electronic systems. These are electronic systems. So, there must be a way, it's like magic. There must be a way to convert chemicals, biochemical or electrochemical changes that happen inside the body to say what can be read in a voltmeter in this case, for example. What can be read in a voltmeter is an electronic current, not an ionic current. So, it achieves almost what is seemingly impossible, that is converting an ionic current into an electronic current. So, these are the special transducers that achieve this. Therefore, you need these special electrodes, special transducers that are also called as electrodes. In this case, because we are interested in measuring these biopotentials, they are called as biopotential electrodes that convert these ionic currents into an electronic current that essentially builds a bridge between the ionic current and the electronic current interface, thus helping us, enabling relatively accurate measurements of bioelectricity and bioelectric signals such as ECG, which is electrocardiography, EMG, electromyography, and EEG, which is electroencephalography. These topics we will look in great detail in future videos and future weeks. So, this is the biopotential electrodes. What is your interest in a biopotential electrode? There must be minimal signal attenuation. I want to have a faithful representation of what is happening inside the cell to be represented in my voltmeter or oscilloscope or some recording system, maybe a DAQ, data acquisition system, and a computer. Faithful representation are minimal signal attenuation, high electrical conductivity is what I am expecting, efficient charge transfer. And I am expecting a relatively low impedance, because at the electrode skin interface, if the electrode itself is causing an impedance, it is going to cause a loss of signal loss, and thus reduce the signal to noise ratio. So, you are interested in having a low impedance at the electrode skin interface, especially for those potentials that have whose amplitudes are weak. For example, EEG amplitudes are of the order of microvolts, whereas EMG, that is the brain electrical activity potentials, are of the order of microvolts, whereas the heart electrical activity are of the order of millivolts. So, there is a difference. Another expectation is that they should not polarize themselves, because that will add to the potential, right. They should be as non-polarizable as possible. That means they should allow current to flow through the electrode without causing any significant change in the electrode potential, which is why we use noble metals such as silver, gold and platinum as electrodes, because they themselves do not add potential to the, I mean they do add, but the potential added is minimal and minimize motion related artifacts. And on top of this, they should not cause any harm to the human. They should be biocompatible. They should not cause any harm to the human body, and they should not be harmed or damaged by the human body. This is biocompatible. Biocompatibility is a two-way street. So, the electrode material must be safe and non-irritating for contact with biological tissue. Sometimes the recordings may need to be made for several hours. For example, in ICU setting, you may need to make this measurement for several hours. In such settings, it should not cause any abrasion or any irritation or any kind of damage to the skin tissue. These are some of the requirements of the biopotential electrodes. What are these? High electrical conductivity, low impedance, as non-polarizable as possible, and biocompatibility. Now, for example, if you keep an electrode outside the membrane, you have a reference electrode, microelectrode here, and then another recording microelectrode that is just outside the axon. This is a way in which you can keep an electrode outside the neuron or the excitable cell. This is also used quite often. Another method is to send one electrode inside the membrane, cell membrane. This is called internal electrodes, electrode inside the cell membrane. We discuss this internal electrodes and microelectrodes in detail in future videos. Now, what happens at the electrode electrolyte interface? Now, this image I have adapted from the standard medical instrumentation textbook, that is Webster. What happens at the electrode electrolyte interface? So, there are two things that happen that are possible. Oxidation happens at the anode, that is electrons are released, and there is a cation that is formed with some charge, that is oxidation or reduction. Usually both of these happens. Usually at the electrode electrolyte interface, both of these happens, both oxidation and reduction happens. Okay. So, this conversion from ionic current to electronic current can be considered somewhat similar to, for example, a foreign exchange. Let us say you are at an airport in an international destination. You would like to convert your currency to that country's currency. For example, you are interested in converting rupees to dollars or dollars to rupees, for example. Now, there is a process for that. There is a foreign exchange counter. There is a booth that sells the other foreign currency, for which you can get there is a business model, they take some commission, whatever, that is beyond the scope of this course. The point is that there is an exchange. Both of these are valid forms of currency, but in different locations. So, ionic current is what happens inside the cell, electronic current is what happens in the electronic devices. So, fundamental one way to visualize this situation. So, both oxidation and reduction happen at the electrode electrolyte interface, right. So, this is the space, the electrode electrolyte interface is the space where this ionic concentration or ionic conduction that is happening inside the cell is somehow transformed into the electronic conduction in the electrode. You would imagine that, oh, maybe electrons are entering the metal. No, that does not happen. What happens is a complex bilayer happens. So, there is a positive, this layer is surrounded by a negative, and so on and so forth. So, that means that there will also be capacitive effects that come into the picture. We will discuss this in future. No? So, at the interface, oxidation, reduction, both of these happens. At the anode, oxidation happens. In this case, electrode loses electrons. So, these metal atoms become cations. Now, that is possible. Abrasion of the electrode and becoming a cation, and that cation moving within the electrolyte is possible. This occurs when the current flows from the electrode to the electrolyte. When the current is flowing from the electrode to the electrolyte, oxidation reaction dominates. When current is flowing from the electrolyte to the electrode, what happens is reduction happens, or reduction reaction dominates, that is cathodic reaction. Electrode gains electrons. So, the cations from the electrolyte are reduced and they essentially get deposited on the electrode, on the metal electrode. Note that a fundamental requirement is that these metals should not be dissimilar to each other. Only some specific metals and materials can be used for this purpose. You cannot have materials or metals that are completely dissimilar to each other and expect these reactions to happen. No, that is not possible. So, there are some requirements for this. So, cations from the electrolyte are reduced and they deposit on the electrode, and this occurs when current flows from the electrolyte to the electrode. In reality, both of these reactions can happen depending on the situation. So, in reality, both oxidation and reduction can happen in the same electrode depending on the direction of current. Note that there are other things that are there in the picture that we have not discussed, but we will discuss in future. Edit this. So, there are these errors that could happen in measurement, those are called as over potentials. We will discuss this in detail in future videos. There are three types of these. These are called as ohmic over potentials, concentration over potentials, and activation over potentials. Okay. We will discuss this in greater detail in future videos. So, this is what happens in the electrode electrolyte interface. So, when you dip a metal into an electrolyte, what is formed is not a trivial oxidation reduction reaction alone, but rather what is actually happening is a bilayer, is a two layer or a charged double layer that is formed. So, there will also be some capacitive effects. That means that when you say that there is a capacitive effect, from our understanding of electronics, you can immediately realize that there is going to be some frequency dependence, something that we will discuss in future videos. Right. So, another possibility, another related, different but not unrelated concept is the concept of half cell potentials. This is a potential difference that is established, that is always there between an electrode and the surrounding electrolyte, that is dependent on the metal, the concentration of ions in the solution, and the temperature, and some other second order factors. Now, for it turns out that it is not so trivial to identify the half cell potential, because there is no way for me to measure the absolute half cell potential of a given electrode, because I have to measure this only using another electrode. Now, I do not know the half cell potential of that electrode, and then this process repeats infinitely. So, it is impossible for us to determine half cell potential as an absolute. So, arbitrarily you assume the hydrogen electrode to have 0 half cell potential. How do you know this? You do not know this, you just assume this. You just assume, or you just set the hydrogen half cell potential to be 0, or half cell potential of an hydrogen electrode to be 0, and then measure the half cell potentials of all other electrodes with respect to this hydrogen electrode. Right? Other half cell potentials essentially are can be measured as a potential difference with respect to this electrode. Why is this happening? Already I mentioned, because there is a charge separation that happens when this metal is energized. Whenever this metal electrode is energized, depending on the charge, there is a charge separation that is created, causing oxidation or reduction reaction at the electrode-electrolyte interface, leading to a double layer of charge, similar to what you would observe in a capacitor, or similar to what exists in an electrically active biological cell membranes. Now, the question is, why do you assume that the hydrogen electrode have 0 volts of half cell potential? Because it is a stable, reproducible and convenient baseline, also an assumption. And since it involves only protons and hydrogen gas, because hydrogen H plus, right, hydrogen ionic electrode, right, H plus essentially involves only protons and hydrogen gas, it is relatively simple to replicate. So, that is why hydrogen electrode has been assumed to have a half cell potential of 0 volts, and all other half cell potentials will have to be measured with respect to this. If I know one other, for example, I have a silver chloride electrode whose half cell potential I know, then and I am interested in knowing the half cell potential of another different platinum electrode, I can then use this half cell potential to compute this half cell potential. But first I need to find out the half cell potential of this silver chloride electrode using the hydrogen electrode. So, that is how you measure the half cell potential. Why is this happening? Due to the charge double charge layer, similar to what you observe in a biological material, similar to what you would observe in a capacitor. The details of this we will see in future classes. So, with this we come to the end of this video. In this video, we looked at biopotential electrodes, electrode-light interface and half cell potential of electrodes. With this, we end this video. Thank you very much for your attention.